6.5 part 2, we're going to talk about integration by substitution. Super similar to what we did in part 1. The difference is now we're using definite integrals. So our definite integrals are going to have a value on the integral. So we solve them the same way we did before we learned about substitution. We are going to differentiate using substitution. We'll plug the x back in, and then we will find f of b minus f of a. All right, so with example 1, what are we going to let u equal? 2x minus 1, perfect. And then du would equal bless you, 2 dx. So this one's kind of like the tricky one that we did yesterday where we have an extra x in our equation here. So I'm going to put a 2 because we need a 2 dx. So that also means that I have to put a 1/2 on the outside. But since I have that extra x here, what do I have to do to find what's going to go into x? We need to find what x equals. So I'm going to take my equation here, find what x equals. So I'm going to solve for x. So I'm going to add 1 to both sides. So we get u plus 1 is equal to 2x. And then divide by 2. So we get x equals u plus 1 over 2. So let's plug in what we have. So 2x minus 1, we're going to substitute the u into there. 2 dx is going to turn into du. And then x is going to turn into u plus 1 over 2. So I have 1/2 times our integral of u plus 1 over 2 over, I'm going to say u to the 1/2 power just to change that square root, times du. What do I do when I have a fraction and a fraction? Keep, change, flips. We're going to keep the top, change to multiplication, and we're going to flip our denominator. So u to the 1/2 power is like a whole number right now. It's like u to the 1/2 power over 1. When we flip it, it becomes 1 over u to the 1/2 power. So then when we simplify, we get 1/2 times our integral of u plus 1 over 2 u to the 1/2 power du. Now this 2, if we want to, since we're dividing by 2 or multiplying by 1/2, we can put it out front. So I can pull out another 1/2, and we have 1/2 times 1/2, which would turn into 1/4. So 1/4 times our integral of u plus 1 over u to the 1/2 power du. Now, if we didn't have this same exact question on the last test, we had something super similar. What would we do next? We haven't taken our integral yet, so we can't plug back in 2x minus 1. How would I simplify to then take my antiderivative? We could call this 1/4 times the integral of u over u to the 1/2 plus 1 over u to the 1/2 du. So we can split it up. Now, how would I combine these together? Awesome. We can subtract. So our exponent on top is 1 minus the 1/2 from the bottom. So 1 minus 1/2 would be 1/2. So we have u to the 1/2 power plus, here we're going to do the same thing, bring the u to the 1/2 power up. So it'd be u to the negative 1/2 power du. Now we can take our integral. So we have 1/4. This would be u to the 3/2 times 2/3 plus u to the 1/2 times 2. And now this is from 1 to 5, but 1 to 5 is our x values. So in order to find out what we have from 1 to 5, we would have to plug back in our x's. We could also do this a different way by keeping it with u's, but we have to find out the u equivalent values of 1 to 5. So what we could do, you could do it either way. You can plug back in your x's and then plug in 1 to 5. Or we could find out what u is equal to when x is 1 and what u is equal to when x is 5. So we're going to do that. So when x is 5, let's find out what u equals. So I'm going to plug 5 into my x here. So u would equal 5 times 2 is 10, minus 1 would be 9. And then when x is 1, let's see, what does u equal? When I plug in 1 into my x here, we would get to minus 1, which is 1. So if I kept it with u's and didn't plug back in my x's, I would have my integral from 1 to 9. These are the u values. So if we are plugging into our u, we need u values. So now we can plug in. When we took our integral, when I added 2/2, we got 3/2 and then divided. Before I plug in the 9 and the 1, I'm going to distribute this just to make it a little bit easier. So this would turn into 1/6 times u to the 3/2 power plus 1/2 times u to the 1/2 power. From 1 to 9. Which one would we plug in first? 9. So when I plug in 9, I get 1/6 times 9 to the 3/2 power plus 1/2 times 9 to the 1/2 power minus, then we're going to plug in 1. So we get 1/6 times 1 to the 3/2 power plus 1/2 times 1 to the 1/2 power. So from here, we just have to solve. 9 to the 3/2 power is the same as saying the square root of 9 cubed. So the square root of 9 is 3, and 3 cubed is 27. So we get 27/6, which would simplify to 9/2, because we can divide them both by 3. Then 9 to the 1/2 power is the same as saying the square root of 9, so that would be 3. So we would get 3/2, because it's 3 times 1/2. We can add these together. We would get 12/2, which is a nice whole number of 6. Let's do the same thing with our right side when we plugged in 1. So I have that minus in the middle. 1 to the 3/2 power would just be 1 times 1/6 would be 1/6. Plus 1 to the 1/2 power is 1 times 1/2 would be 1/2, we need a common denominator here, so I can multiply the top and the bottom by 3. And then when we add, we get 4 over 6, which would simplify to 2 over 3. So we get 6 minus 2/3. Again, we need a common denominator, so I can change 6 to be 18 over 3. 18 minus 2 is 16 over 3. That would be our answer. We can do it either way. So in example 2, and the first one that we did, we left it as x values. That's because we plugged our x's back into the u's. If we don't do that and we left it as u's, we would have to find our u values. So we would take what we're integrating between, so from 1 to 5, and we had to find the u equivalent of each of those. Yes. Yes. So with example 2, we're going to say let u equal what? What's u going to equal here? X squared plus 1, perfect, the inside. X squared plus 1. Then du, so the derivative of u would be 2x dx. So I have an x and a dx, but I'm missing that 2, so what could I do? If I put a 2 on the inside here, what else do I have to do? Put a 1/2 on the outside, perfect. So we have 1/2 times the integration from 0 to 1 of 2x dx is going to turn into du, so we have u cubed du. So now we're going to integrate. So we have 1/2 times, this would be u to the 4th power times 1/4. Now it's from 0 to 1, but I can't quite plug in the 0 to 1 until I plug back in the x's. So I'm going to call this 1/8 just to simplify a little bit. And then u, we're going to substitute back in our x squared plus 1 to the 4th power. Now it's from 0 to 1. So we can't plug in 0 to 1 until we plug back in our x's. 0 and 1 are x values, so those have to get plugged into x. So which one would we plug in first, 1 or 0? 1. So you have 1/8 times 1 squared plus 1 to the 4th power. We can evaluate what this is. I'm just going to write out what we would get when we plug in 0 too. So minus 1/8 times 0 squared plus 1 to the 4th power. So let's figure out what we get when we plug in 1. So 1 squared plus 1 would be 2. 2 to the 4th power is what? 16. So we get 1/8 times 16, which would be 2. Minus, here we would get 1 to the 4th power, which would just be 1, times 1/8 would just be 1/8. So we have 2 minus 1/8. We need a common denominator. So I'm going to make 2 16 over 8. So this would turn into 15 over 8. So that would be our answer. Next, we're going to talk about integration of even and odd functions. So on this page, it gives us an example of an even function. An even function is symmetrical about the y-axis, and odd function is symmetrical about the origin. When we have an odd function, if we were finding the integral from, here it says a to negative a, if we were finding the same amount in the positive direction as we are in the negative direction, and we have a positive and a negative, our area, or our integral, would be 0 here, which we'll talk about on the next page. It gives us the theorem. If it was an even function, I could find what my integration is from 0 to a, and then we would just multiply that times 2 because we're going to have the same amount above the x-axis on both sides of the y-axis. So that's explained on the next page. If it's an even function, instead of taking our integral from negative a to a, we could take it from 0 to a and then just multiply our integral times 2. If it's an odd function, we can take our integral from negative a to a, and that would just equal 0. Example 4. Example 4, it's either going to be an odd function or it'll be neither, because we see our highest degree is x to the 5th power, so it's definitely not going to be an even function. But we can figure out if it's going to be an odd function or not. We can use the shortcut. I think we did this in the beginning of the year, determining if a function was even, odd, or neither. A little shortcut that we could do is we can plug in the same number and its opposite and see if we get opposite values. So I could plug in 2 and negative 2 and see what we get. If we get opposite answers, then we know this is an odd function, and then our integral would just be 0. So if I plugged in 2, 2 to the 5th power would be 32 minus 4 times 8 would be 32 plus 6 times 2 is 12, so we get 12. Then if we plug in negative 2, this would be negative 32. Then we would get negative 8 times negative 4, so plus 32. Minus 12, so we get negative 12. Since these are opposite answers, we know that this is an odd function. So our integral would just equal 0. So because we have the same amount in the negative direction and the positive direction, our area or integration would just be 0. So since these were opposites, we know that it's an odd function. If we got the same answer, then it would be an even function.
So it doesn't necessarily have to be the two numbers there, it could be any opposite.
Any opposite, yeah. So looking at example 5, I'm going to simplify. So I'm going to distribute, so we get x to the 4th power plus x squared dx. We could just as easily take the integration and plug in our values from negative 4 to 4. But just to show if this is an even or odd function, it's either going to be even or neither here because our highest degree exponent is 4, so it's definitely not an odd function. So I can plug in a number and its opposite, so we could plug in 2 and negative 2. When I plug in 2, 2 to the 4th power is 16, plus 2 to the 2nd power is 4, so this would be 20. And then when we plug in negative 2, we would get 16 and plus 4, so that would also be 20. So since these are the same answer, then we know that it is an even function. When it's an even function, we can take our integral from 0 to 4 and just multiply it by 2. So we still have to find what our antiderivative of x to the 4th power plus x squared. But we can make the math a little bit easier for us just by integrating it from 0 to 4 and multiplying our answer by 2. So when we take our antiderivative, we get x to the 5th power times 1 over 5 plus x to the 3rd power times 1 over 3. Multiplying this times 2 from 0 to 4. Now we can save that 2 for the end. We can find what our answer is and then just multiply our answer by 2. So we could plug in 4. So we get 1/5 times 4 to the 5th power plus 1/3 times 4 to the 3rd power. What makes this a little bit easier when we can just multiply it by 2 instead of then plugging in negative 4 is when we subtract 1/5 times 0 to the 5th power plus 1/3 times 0 to the third power. We know that this is just going to be 0. So it kind of cuts the math in half for us. So from here we can just evaluate. 4 to the 5th power is 1024 over 5. 4 to the 3rd power is 64 over 3. Find a common denominator, add these together, multiply by 2.